On April 7, 2026, Google published a paper in Nature, not a press release, not a marketing announcement, a peer-reviewed scientific paper in one of the most respected journals in the world. And buried inside the careful academic language of that paper was a sentence that should have stopped every scientist, every engineer, every person who understands what it means, in their tracks. For the first time in the history of computing, a quantum computer had run a real, verifiable algorithm and produced a result that the world's most powerful supercomputers could not match, not in theory, on hardware, in a laboratory, with results that could be independently checked and confirmed. The word that matters in that sentence is verifiable, because every previous claim of quantum supremacy, including Google's own 2019 announcement, had one problem that critics never let die. The problems those quantum computers solved were designed specifically to be hard for classical computers and easy for quantum ones, with no practical application to anything in the real world, and no way to confirm the quantum answer was actually correct, without using a classical computer that was too slow to compute it. Google's 2026 result is different in a way that changes everything, and if you do not understand why that difference matters, by the end of this video you will. But here's the thing about April 7th that most coverage missed entirely. The Quantum Echoes paper was not the only thing Google published that week. On March 30th, 8 days earlier, a separate team at Google Quantum AI published a second paper that set off a completely different kind of alarm bell. That paper showed that breaking Bitcoin's encryption might require 20 times fewer qubits than anyone had previously calculated. That result, combined with concurrent research from a startup called Day or Atomic, that used artificial intelligence to discover new quantum attack algorithms, prompted the CEO of Cloudflare to announce an accelerated deadline for quantum-safe security. Cloudflare secures a significant fraction of all internet traffic. Its CEO said publicly that the new results were, quote, a real shock, and that the company would need to speed up its efforts considerably, moving its own preparation deadline to 2029, the same week that Google proved quantum computers can do useful things faster than any classical machine. It also showed that the timeline for those machines to break internet security is collapsing faster than anyone expected. That is not a coincidence. That is a reckoning. Let me walk you through what Google actually did in April 2026, because the Quantum Echoes breakthrough is genuinely remarkable and deserves to be understood rather than just celebrated. Google's quantum chip, called Willow, has 105 qubits. To understand why that matters, you need to understand the error problem that has plagued quantum computing since its inception. Qubits are extraordinarily fragile. Any interaction with the outside environment, a vibration, a stray particle, a tiny fluctuation in temperature, can cause a qubit to lose its quantum state in a process called decoherence, and the more qubits you connect together, the more opportunities there are for errors to accumulate. For decades, this was the central unsolved problem in quantum computing. You could build a small quantum processor with a few dozen qubits that worked reasonably well. But every time you tried to scale up, the error rate scaled up too, and the computation became unreliable before it produced a useful answer. It was like trying to build a cathedral out of sand. Every brick you added made the foundation shakier. Then in December 2024, Willow demonstrated something that had been a theoretical target for 30 years, but had never been achieved in hardware. It showed that as you increase the size of the error-correcting code protecting the quantum calculation, the error rate goes down rather than up. This is called below-threshold quantum error correction, and it means that building a larger quantum computer does not automatically make it noisier. It can make it more reliable. That 2024 results changed the physics of what is possible in quantum computing. The April 2026 Quantum Echoes result is the first demonstration of what that improved error correction can actually do on a real problem. The Quantum Echoes algorithm is based on a concept called an out-of-time order correlator. The name is technical, but the intuition is beautiful. Imagine sending a carefully crafted signal into a quantum system, then deliberately disturbing one small part of that system, then running the entire process in reverse to listen for the echo that comes back. In a classical system, this echo would be completely scrambled by the disturbance, unreadable, lost. In a quantum system, the echo contains information about how the disturbance spread through the entire system, revealing hidden structure about how quantum information propagates. This is genuinely useful for understanding molecules, materials, and fundamental quantum physics in ways that classical computers cannot access, because the simulation itself is inherently quantum mechanical. Google ran this algorithm on Willow using 103 qubits in forward and backward evolution sequences of extraordinary complexity. The result was 13,000 times faster than the best classical algorithm running on one of the world's most powerful supercomputers. And critically, the result was verifiable. Another quantum computer of similar capability can run the same algorithm and get the same answer. This is not a speed comparison on an artificial benchmark. It is a reproducible scientific result that produces genuine information about the physical world. Site index equals 56 greater than Google's team described this as the first time in history that a quantum computer had successfully run a verifiable algorithm that surpasses the ability of supercomputers. Site Google CEO Sundar Pichai said the outcome represents a verified milestone toward the first real-world quantum applications. Site index equals 54 greater than across Willow's entire 105-qubit array. The chip features fidelities of 99.97% for single-qubit gates, 99.88% for entangling gates, and 99.5% for readout. Cite those numbers represent the precision of every quantum operation the chip performs. To run an algorithm of the complexity of quantum echoes, every gate operation must work correctly with extraordinary reliability, and Willow delivers that reliability at a scale that previous systems could not. Now I want to explain why the practical application matters as much as the benchmark performance. Because this is where Google's April 2026 result separates itself from every previous quantum milestone. In the same week as the Quantum Echoes paper, Google published a second proof-of-principle experiment in partnership with the University of California, Berkeley. They used the quantum echoes technique to study the molecular structure of real organic molecules dissolved in liquid crystal. Using nuclear magnetic resonance data from the Pines Magnetic Resonance Center at Berkeley, the quantum simulation not only reproduced the results that traditional NMR spectroscopy had already found for these molecules, it also revealed structural information about the molecules that NMR alone could not easily provide. The quantum computer was not just fast. It was finding things that classical tools could not see. Drug discovery depends on understanding how molecules fold and interact. Designing new materials depends on understanding quantum mechanical behavior at the atomic scale. Quantum computers that can reveal molecular structure information beyond what classical instruments provide are not a future possibility. As of April 2026, they exist, they work, and they are already being tested on real scientific problems. Google has also made a strategic move that changes the shape of the quantum competition going forward. On March 24, 2026, 13 days before the Quantum Echoes publication, Google announced it was adding neutral atom quantum computing as a second hardware modality alongside its existing superconducting qubit program. This is a significant strategic expansion because the two approaches have complementary strengths. Site index equals 41:1 superconducting systems execute millions of gate operations in rapid succession, with each cycle taking about a microsecond, optimized for speed and repeated operations. Neutral atom systems operate more slowly, but can scale to far larger numbers of qubits. With arrays of roughly 10,000 qubits already demonstrated in research settings, and offer any-to-any connectivity, meaning qubits can interact more flexibly. Site Google is simultaneously pursuing the approach that is fastest and the approach that can be largest. Hartmut Neven, the founder of Google Quantum AI, wrote that superconducting processors are easier to scale in the time dimension of circuit depth, while neutral atoms are easier to scale in the space dimension of qubit count, and that investing in both approaches increases the ability to deliver on their missions sooner. When a company with Google's resources commits to running two parallel quantum hardware programs simultaneously, it signals a level of institutional conviction about the technology's commercial timeline that is worth taking seriously. Now I need to bring you back to the other paper, the March 30th paper. Because the quantum echoes result and the encryption threat result are not two separate stories. They are the same story viewed from two different angles. Both are the story of quantum computers reaching a new level of practical capability in 2026 that changes what is possible. Site index equals 42:1 greater than Google's paper. Unshore's algorithm showed those circuits could be executed on a superconducting cryptographically relevant quantum computer with fewer than 500,000 physical qubits, roughly a 20-fold reduction from prior estimates. Cite 500,000 physical qubits sounds like a lot. Current quantum computers have hundreds to low thousands of physical qubits in their most advanced systems. But the direction of the curve is what matters. Every year, qubit counts increase. Every year, error rates improve. Every year, algorithmic efficiency advances. As March 2026 demonstrated dramatically when Oratomic's team used AI to discover a new quantum attack algorithm that nobody had found before. The Oratomic team was explicit about this. They stated publicly that artificial intelligence was instrumental in developing their algorithm, that there was, quote, no question at all that AI was used to accelerate this development. The convergence of AI and quantum computing as mutually accelerating technologies is something that the security community had theorized, but that 2026 showed happening in practice. Site index equals 44:1 greater than Google's. VP of Security Engineering Heather Adkins wrote publicly that systems should now transition to post-quantum cryptographic security by 2029. Cite. That statement from Google's own security leadership, published in the same week as a quantum breakthrough paper, is not a coincidence. Google knows both sides of this equation because it is building both sides of this equation. It knows how fast the hardware is advancing because it is building the hardware. It knows how much the algorithmic efficiency improved in March 2026 because its own researchers found the improvement. And it is telling you that you have 3 years to prepare. Site index equals 45:1 Cloudflare, which secures a significant fraction of internet traffic. announced it was accelerating its deadline to prepare for quantum computers to 2029, with a researcher describing the new results as a real shock requiring considerably speeded up efforts. Site Cloudflare is not a company that makes dramatic public statements about security timelines for attention. It is a company that handles the security of a large fraction of internet infrastructure and takes public communication about threats seriously. When Cloudflare says 2029, it means its engineering teams have done the math and decided that timeline is operationally credible. The cryptocurrency implications of the March 30th paper deserve specific attention because they are the most concrete near-term financial risk that the April 2026 developments create. Site index equals 46:1. Google's findings prompted Ethereum researcher Justin Drake to describe the publication as a monumental development, estimating a meaningful chance a quantum computer could break elliptic curve keys by the early 2030s, while also highlighting technical nuances, including that some systems could theoretically crack keys in minutes, while others might take days. Cite the detail about minutes matters enormously. Site index equals 46:1. Alex Pruden, CEO of Project 11, argued that a 9-minute crack is faster than Bitcoin's average 10-minute block time. Site meaning a sufficiently capable quantum computer could theoretically intercept a Bitcoin transaction, derive the private key from the public key that becomes visible when a transaction is broadcast, and redirect the funds before the transaction is confirmed on the blockchain. This is not the scenario of quantum computers breaking long-stored encrypted data over years. This is the scenario of real-time theft from active transactions. The cryptocurrency ecosystem's transition to post-quantum cryptographic standards requires consensus across decentralized networks that is structurally harder to achieve than centralized systems updating their infrastructure. That structural difficulty, combined with a compressing timeline, represents a genuine financial risk that the crypto market has not priced in. The honest summary of where Google's 2026 results leave quantum computing is this: the breakthrough happened. Not the final breakthrough, not the fault-tolerant large-scale machine that cracks RSA-2048, not the system that renders all current encryption immediately obsolete, but the breakthrough that proves the path is real. The hardware works at the level of precision required for genuine scientific utility. The error correction improves as you scale up rather than degrading, and the algorithmic efficiency is advancing faster than classical computers are defending against. Google's roadmap places its next milestone as a long-lived logical qubit, which is the step between where Willow sits today and the fully fault-tolerant systems that represent CUDA hardware. The IBM roadmap places full fault-tolerant systems in 2029. Google's own warnings about encryption migration point to 2029 as a deadline. These are not arbitrary numbers. They reflect the genuine technical assessment of the people who are building this technology. What April 2026 proved is that the quantum era is not something that will begin someday. It began. The world's most powerful classical supercomputers were beaten by a quantum chip on a real scientific problem. The result was published in Nature, independently verified, and repeated. The same company that produced that result simultaneously showed that the algorithmic path to breaking internet encryption requires 20 times fewer resources than anyone calculated before. And artificial intelligence is now accelerating quantum algorithm discovery in ways that human researchers alone could not match. All three of those things happened in the same 2-week period. That is not incremental progress. That is a phase transition. The question is not whether to pay attention to this. The question is whether you understand what it means before it becomes impossible to ignore. If this gave you a clearer picture of what Google actually achieved in April 2026 and why it matters, beyond the headlines, tell me in the comments which part landed hardest. Was it the quantum echoes verifiability breakthrough, the 20-fold reduction in encryption attack resources, or the AI-accelerated algorithm discovery? I read every comment. And if you want to understand exactly how far the other quantum competitors, IBM, Microsoft, and China, are behind or ahead of Google right now, that is the next video. Subscribe so you are there when it drops.